we're still doing work integrals using path independence. And I'm just doing more examples, especially of what I call the easy way. Let's say we're given this problem. And by the way, the format of the problem itself kind of gives it away that this is a path independence problem because it doesn't give us the path. It just gives us where it starts and where it stops. So we're figuring it's a path independence problem. So let's go for the gusto and try to find the phi, and I'll use the easy method for that. Here is our p. It's what's in front of the dx. Here's our q, and here's our r. Integrate the p with respect to x. I get an x squared sine y plus x e to the 3z. For the q, I'm integrating this with respect to y. I'll get x squared sine y. And this, I'll integrate with respect to z. I'll get what? X e to the 3z plus 5z. I want to add up all these terms, but I cut out the repeats. This term repeats with that term, so I only want to include one of them. So the whole phi will be x squared sine y plus x e to the 3z plus this guy. Oh, this is another repeat. This term repeats with that term. So I actually have two repeats here. So this is the whole phi plus that 5z. I don't include this because it's already included here. I don't include this because it's already included. So here's my phi, and now I must check it. If I don't take the curl to check it, I got to do this. Is this grading? Is the grading of this phi equal to our f? I won't go through that, but yes, it is. Do some more stuff. Here's our p, here's our q, that's all you have. Integrate this with respect to x. I'll have sine x cosine y. Integrate this with respect to y. I have y plus sine x cosine y. So they both have sine x cosine y in them, so I only include it once. So this is my whole phi. Got it? And again, we check, and lo and behold, the gradient of that is indeed equal to f. You could have checked it without taking the whole, well, it's only 2D, so that this is also true. Partial of p with respect to y equals the partial of p with respect to x. Let's see, should I go through this? Part B was also do it the normal way and use whatever path you want. Well, the easy path, I think, is to just cut a straight line that goes between these 2 points. And let's see, that would be y just stays at 0 the whole way. So y equals 0 and dy equals 0. I use the substitution method. This whole second term goes away. This y is a 0, so cosine y is just 1. So it's just cosine x dx. X goes from 0 to pi over 2. Take that integral, I get a 1 that way. I didn't finish the other easy way. Once I found the phi, I evaluated it at the 2 points. It's the stopping point, which will be pi over 2, 0. Starting point is 0, 0. So it's phi at the stopping point minus phi at the starting point. Don't get those backwards. And I won't go through that substitution and evaluation. It's pretty easy. Let me modify that example by just a sign. Let's say we're given this problem. All I did was change one sign. Here's our f. And when I do that, integration. Here's what I get for the X part. Here's what I get for the Y part. When I say they're the same term, that means everything's the same, including the sign. This sign is different from that sign. This is a plus sine X cosine X. That's is a minus sine X cosine X. So I add them all up and I just get Y. And then when I check, see if the gradient of that equals F, no, it does not equal F. And if I check this other condition, I see that that's not true either. This is not a conservative vector field. I could still get a phi, but it's not the true potential. This guy's gradient does not equal F. You could find a phi, but if its gradient doesn't equal F, you don't have a conservative vector field, and you can't use this method. Oh, let's do another example. I got time for this? Let's see. Here we go, and once again, it's kind of given away that it doesn't give you the path, it just gives you the start and stop. Probably kind of figure that it's a path independence problem. Here's what I like to pull the F out and work on this. There's my P, there's my Q, there's my R. Just put it in a vector. Integrate this guy with respect to X, it's square. Integrate this guy with respect to Y, it's YQ. With respect to Z, it's Z to the fourth. Check its gradient. Lo and behold, it does equal the F. You could also do the curl, and it should be 0. And how do you evaluate this integral? It'll be this phi. Oh, don't look at that. This thing. It'll be this phi. In fact, that's a mistake students did on exams, and I almost do it sometimes. You're evaluating phi, not the gradient of phi. Evaluate phi at 1, 1, 1, and then minus phi at 0, 0, 0. Do all those, plug them in, make those substitutions, you get an answer. By the way, if P is solely a function of X, Q is solely a function of Y, and R is solely a function of Z, like in this case, F is always conservative, and it's a one-line proof that you can take the curl, and it's always going to be 0. You might want to put that in your hip pocket. I'll probably finish this up in another video. So it'll take 3 videos to do path independence. One's starting to come through the window here.